Next section on the waves, it's going to be standing waves on stretch strings. But before, we have already discussed a little bit about the standing waves formed on stretch strings in the previous lesson. We did a lot of analysis. So here we won't be analyzing that again, but let's do a quick summary. But before we move on to that, I have to teach you one more topic, then it will be easier for us to understand the rest of the theory part. This is that section, speed of transverse wave on a string. So, the previous tutors we learned, then there is a stretch string like this, and when you pluck that string, standing waves will be created like this. Those standing waves are actually created due to the interference of two waves which are traveling in opposite directions, two coherent waves which are traveling in opposite directions. When you pluck a string like this, the particles of the string vibrate like this in the direction perpendicular to the propagation of the wave. So, those waves are transverse waves. Now, here we are not going to derive any equation. This equation you just have to remember this. So, I will introduce the equation. Well, this is that equation, V equals square root of T over M. You might have seen this equation in dimensions, unit and dimensions under dimensional analysis. See if you can recall that. So, this is the equation, you just have to remember it. The factors, the only two factors which are going to affect the speed of transverse wave along a string are tension acting on the string. Unless the string is stretched, there won't be a wave formed in the string because it has to be stretched. If it is taut, waves can't be formed. So, there is definitely going to be a tension, and this M is called, it is not mass, it is mass per unit length, because string is it is very thin. So, 1 meter of that string, what is the mass? That is this. Now, we will quickly with the units. Now, speed of transverse wave, it is meters per second. For tension we normally use Newton, and for mass per unit length, mass per length, so it is going to be kilograms per meter. Okay, right. So, you always know that we have introduced an equation without deriving it. So, when you do that, we always have to check whether that equation is dimensionally accurate. Okay. For that, what do? We have to prove that the dimensions of the left hand side should be equal to the dimensions of the right hand side. So, let me quickly do that here. So, let us start. The dimensions of left hand side, LHS, left hand side. So, that is going to be equal to dimension of speed, correct. So, what are the dimensions of speed? It is L t minus 1, okay, good. The dimensions of right hand side, that is going to be equal to dimensions of square root of t over m. And what are the dimensions of t? That is tensile force. So, it is square root m L t minus 2 over m is mass per unit length, that is mass over length. So, that is going to be m L minus 1, all right, good. So, what is going to happen? This m and this m are going to be cancelled off, and finally, we will be getting an equation like this, square root of this L minus 1 will go up. So, it becomes L squared t minus 2. So, the answer is, when you take square root, it is again L t minus 1. So, left hand side dimensions are equal to right hand side dimensions of the equation. So, from that you can say, hence the equation is dimensionally accurate. Perfect. All right, fine. Before I move on to the next part, there are some more things you have to analyze. This mass per unit length, this is something new we have come across. Let us do a small analysis about that as well. So, when we talk about mass per unit length, simple m. Now, mass per unit length, the equation is going to be mass divided by length, correct. Now, what I am going to do is I am going to derive an equation for this, another equation. For mass, I can say mass is actually volume multiplied by density divided by length, agreed, right. Now, for volume, we can write length into cross sectional area. Instead of using these terms, I will use the symbols now. So, for volume, I can say length multiplied by area, that is the volume, multiplied by density, we normally say rho, divided by length again L. Okay, I hope it is accurate, good. Now, L, length and length will get cancelled off. Finally, we will end up in an equation like this, simple m is equal to A rho, where A is the cross sectional area, rho is the density, okay, fine. If you want to further develop this equation, still yes, you can do it. What is that? Now, this equation can be written like this also, mass per unit length is equal to area is the cross sectional area. So, if you take a string like this, the cross section area is what? A circle, right. So, for area I can say pi r squared rho, where r is the radius of the string, which will be very small. Okay. If not, if you want to develop it further, you can still write m is equal to pi d squared over 4 rho. What did I do there? Instead of area, I have written pi d squared over 4, where d is going to be the diameter of the string. Okay. So, these equations are also important. You need to know these relationships for mass per unit length and the radius and diameter. So, this is the analysis about mass per unit length. Okay. Now, in the previous lesson under standing waves introduction, we discussed a little bit about the type of standing waves formed in a string. Now, we discussed about three standing waves. It is not just 3, there can be a lot more, but we just discussed standing wave with 1 loop, standing wave with 2 loops and standing wave with 3 loops. Okay. Now, we just discussed during each quarter of an oscillation how the particles are going to be arranged. Okay. We are not going to repeat that, but let us do a small summary and try to understand how the particles are going to oscillate overall. These are the 3 standing waves, the 3 initial standing waves. There can be 4 loops, 5 loops, 6 loops, 7 loops, does not matter, but these are the 3 most fundamental standing waves which are formed in on a string. Right. Now, if you take this case, we can see the particles are oscillating at different amplitudes. So, if you consider the particles on this string, in this case all the particles are oscillating in this direction. That means perpendicular to the direction of propagation of wave. Here also same, but here there are 3 nodes actually. Here there are 2 nodes, here there are 3 nodes, here there are 4 nodes. So, in the middle there will not be any particle which is not oscillating, but here there will be a particle in the middle which is not oscillating. Here also there will be 2 particles which will be at rest without oscillating, but the rest will be oscillating. Let me explain, let me illustrate that with another diagram below. This is a representation of how the particles in the medium are going to oscillate when these standing waves are formed. Okay, I think we discussed this, but we did not discuss this. Sometimes in MCQs and all, you might have to plot this. So, to get a better idea, I will just draw the outline of the standing wave too, so that it will be less confusing. Alright, different particles oscillate at different amplitudes, something like this. Okay. So, this is the basic idea about the speed of transverse wave on a string, and then the way the particles oscillate when a standing wave is formed. Now, we are going to see, we are going to analyze these in depth. Okay. And we are going to derive an equation also. So, next what we are going to do is we are going to fill this table, standing wave patterns on a string, and the columns. Look at the columns, the wave pattern, how the wave looks like, then the type of wave, there is a name for each wave, and then harmonic, which harmonic is that, we will discuss about this, frequency, what is we can talk about when it is a wave, we can talk about frequency, we can talk about wavelength, and we can talk about nodes and antinodes, how many nodes are there, how many antinodes are there, everything we can discuss. Now, you have to understand one thing, in this the wave is, now there is a string, a stretch string. So, first of all let me draw a string where there is no wave created. So, this is that string, there is no wave on this string. Okay. Right. And so I am going to establish certain things. We are not going to change the string. Can you remember this equation now? We learnt V equals square root of T over M. The equation is for speed of transverse wave along the string. Okay. So, we are not going to change the string. So, M is constant, M is mass per unit length. If you do not change the string, it will not change, and we are not going to change the tension acting on the string. We have pulled it and fixed it. So, we are not going to change the tension on the string. So, if you maintain these two constant, V is going to remain constant. Now, these two are constants, hence V is also going to remain constant for this analysis. Keep that in mind. Right. Now, if V is constant, we know that V is equal to F lambda. If F is changed, lambda is going to change. Okay. So, first we have to establish that. Now, this is the string, and before we move on, there is no wave here. So, initially we have start at 0, nothing here, no wave, and most important thing is the length of the string. So, I will mark the length of the string. Let us take the length of the string as L. That also is a constant. We will not be changing the length of the string because it is fixed to two boundaries. We will not be changing that length throughout this experiment. Now, what we are going to do is we have actually fixed this string to a vibrator, okay, to a vibrator here, let us say here to a vibrator, where you can increase the frequency of that vibrator from 0. So, you slowly start increasing the frequency. As the frequency increases, different types of standing waves will be formed on the string. Right. Now, when you talk about standing waves, what is the most fundamental standing wave which can be formed on a string? That would be this, we discussed in the last week. No standing wave, the first standing wave, then the second standing wave, then the third standing wave. So, if you want to form this, first from 0 you have to increase the frequency at a particular frequency, this will happen. And let us say that is 100 hertz. If I keep on increasing the frequency and when the frequency becomes exactly double, that means 200 hertz, you will get 2 loops. And when you make the frequency 300 hertz or 3 times the initial frequency, we will get 3 loops, like that 4, 5, 6, likewise we will be getting the loops. So, let us draw the waves and let us quickly analyze. I have taken the first 3 waveforms like this. You can draw the waves like this, one like this and one with broken lines, but or else if you want to draw this in complete line, it is still fine. I have been drawing it like that, but sometimes in exams and all we normally draw full lines like this. Both are correct. I just drew like this to give you the indication that this will be this will not stay at one place, it will keep on doing this. So, it will both will appear to us, that is why I drew like that, but there is no there is nothing wrong in drawing the wave patterns like this too. So, in the last tutorials we discussed the 1 loop, 2 loops, 3 loops, and what are the things is change here? The amplitude changes. Okay, all the energy is concentrated to 1 loop, so high amplitude. Energy is distributed, energy is even more distributed. So, as the number of loops increase, the amplitude will change. Now, first one type of wave. Now, I have left this part empty because there is no wave. So, let us start from here. This wave is called the fundamental mode because it is the most basic form. So, fundamental wave or fundamental mode, that is what we call, and this is called the first overtone. Okay, not the, even though that is second, we say first. Now, for example, like we have ground flow, first flow, second flow. Now, first flow is second from the ground, but we do not call it second flow, right. Likewise, this is called the first overtone because the fundamental is reserved, fundamental, then first overtone, then what is this called? Second overtone, third overtone, fourth overtone, it will go on like that. And before I fill this column, I will fill this frequency. For frequency, we normally use for the first one, for the fundamental mode, we use the symbol F0, which is called fundamental frequency, fundamental frequency. Okay, right. Now, I said we will be changing the frequency. Now, this frequency is the frequency of first tone. I will take it as F1, and we know F1 is going to be equal to 2F0. Okay, why? Because if you want to if you want to increase the number of loops, you have to increase the frequency, and if the number of loops become 2, that means if you have double this frequency, this is 100 hertz, this is 200 hertz, and this one it is going to be F2, that is 3F0. I have put F2 because this is second overtone. Okay, you can use your own symbols, it is not a must, this is not a must, we just for the convenience I have used it. Right. Now, this harmonic, you have to be little careful. Later we will learn waves formed inside tubes. I explained a little bit about that, not I mean I did not explain anything, I just said in air also, when air trapped in a tube, what do you call that, standing waves can be formed. There this pattern goes as F0, 3F0, 5F0, not this way. Okay, here it increases methodical 1, 2, 3, 4, 5, 6, it will go on like that, but there it does not happen like that. So, F0, 3F0, 5F0. Now, this harmonic you have to be little careful. Harmonic is given as a number of or as a multiple of fundamental frequency. Now, this is called first harmonic. First harmonic. So, everywhere in any case first one is first harmonic. So, now this is first overtone, but this is not it does not have another name, fundamental harmonic or anything like that, it does not have. We start with first harmonic. This one is actually called second harmonic. Second harmonic, and the other one, there is no surprise, it will be called third. Alright. The term second for this harmonic comes because of this number 2, and term third comes because of this number. in case if this was F0, 3F0, 5F0, this is going to be first harmonic, third harmonic, fifth harmonic. You have to be a little careful there. Here it's very straightforward, but there are some cases, there can be some cases where it will be different. Now, before I go to wavelength, let us finish these two off. It is very easy, right? Number of nodes, how many nodes are there? This point and this point are not oscillating at all. So, there are 2 nodes, and here we have 1, 2, 3 points which are not oscillating. So, 3 nodes, and here we have obviously 4 nodes. You can understand there is a pattern. And what are antinodes? Antinodes are the points which are oscillating at the highest amplitude. So, here we have 1 point, here we have 2 such points, here we have 3 such points. So, 1, 2, 3. Now, I have seen this MCQ where you can say, now look at the harmonics. Harmonics are multiples of antinode, first harmonic, second harmonic, third harmonic. Okay. But how did this, if this is F0, how did this become 2F0 and how this become 3F0? Because of the number of loops. Okay, number of loops, which could have written that somewhere, but it's okay. We'll take number of loops. N will take it as number of loops. That is a very important part. I mean, you can't just ignore it. So, for this one, N is equal to 1. For this one, N is equal to 2, and for this one, N is actually equal to 3. All right, fine. Now, wavelengths. Wavelength is going to be a little bit tricky. Now, the wavelength of fundamental, we will take it as lambda naught. I will mark it like this, and I will come back to that, and he will take it as lambda 1, we will take it as lambda 2. We are going to analyze this lambda naught, lambda 1 and lambda 2. We just say lambda naught, lambda 1, lambda 2. I have left this space to get an equation for these lambdas. Now, the length does not change, right? Length is L. And what is the relationship between length and lambda in this case, if you take this case? All right. So, I will mark the length, I will choose another color, right. Now, this length is L, and there is only one loop. Do you agree with me? There is only one loop, and if there is one loop, what is the length of that loop? We discussed in the previous tutorial about standing waves. If you have one loop, the length of that one loop is given by lambda by 2. The length of 2 loops is only given by lambda. Here, length of 2 loops is only given by lambda. So, here if you take this one, this is actually one loop. So, it is going to be L is going to be equal to lambda naught divided by 2. I hope you understood that. Okay, fine. Now, if you take lambda naught, then L is equal to lambda naught by 2. So, what is lambda naught? Lambda naught is going to be equal to 2L. Yeah, never mind, let us write it here also. Oh no, can't write it like that. I will use another color. I will use this. We just discussed lambda naught by 2 is equal to L. So, lambda naught is actually equal to 2L. Agreed? Yes. And let us move to this part. If you take this part, what is the relationship here? Here L, it is going to be equal to, there are 2 loops, and the wavelength of this part is now since the frequency is different, wavelength will also be different. Okay. Now, the wavelength of this is lambda 1. How many loops are there? 2 loops. So, that should be lambda 1. Okay. Here L is equal to lambda 1, directly we can say lambda 1 is equal to L, right, fine. And here if you take, when you mark the length, L is equal to, now lambda 2, but 1, 2, 3 loops are there. So, when there are 3 loops, you can say 3 lambda 2 by 2. For one loop, lambda by 2. So, when there are 3 loops, this. So, 3 lambda by 2 is equal to L. So, what is lambda 2 then? Lambda 2 is going to be equal to 2L by 3, 2L by 3, and lambda naught. Now, there is an important part I am going to write, see if you can understand. Now, lambda 1 can be written as, I will rewrite it, lambda 1 can be written as 2L over 2, okay, and lambda naught can be written as 2L over 1, okay. There is a reason behind that, I will explain that now. Good. Now, what is happening here? If you say, if you compare these 1, 2 and 3, that is actually the number of loops. See, 1, 2, 3. So, this 1, this 2 and this 3 are the number of loops. So, when you continue drawing more, when you continue to draw more wave patterns, you will end up in another wave which has n number of loops. okay, which has n number of loops. I'll just draw it like this. Let's just consider lots and lots of loops, maybe like this, and I'll just draw in broken lines. And the last one, we don't know how many loops. It can be 50, it can be 25, it can be 100, we don't know. I'll just randomly take like this. Okay, how many loops are there? In n number of loops are there. N is actually n number of loops. Okay, now when you compare the length, what is going to be the length now? Length is L, yeah, no change in that, and the wavelength is going to be n times lambda by 2. We'll take lambda as the common one, lambda by 2. Okay, right. So when you go here, the lambda L is equal to, for this case, L is going to be n lambda by 2. So lambda is actually equal to 2L by n. This is the common equation for lambda. We can derive this common equation. I hope you understood that. But this is where this is what I wanted to derive from all this. Okay, so lambda, you can say the lambda, different lambdas are here, and if you want an easy access to that equation for that lambda, that means you have to multiply this length by 2 and divide by n, where n is the number of loops. Okay, I hope that part is clear. Now let's move on to a very important equation. We are going to quickly derive a very important equation. Yeah, let's see what is that equation. We start at v equals f lambda. This is where we started, right? But we know that v is equal to square root of t over m, that is already derived, and lambda is equal to 2L over n. Okay, so when you can compare all these things, you can come up with an equation like this. What is that equation going to look like? First of all, I'll start here. V equals, instead of lambda, you can put 2L over n. So that's going to be 2L f divided by n. That is first equation you will come up with. Okay, right. And instead of v, let's substitute this. Then you will get root of t over m is equal to 2L f over n. Okay, just small mathematic work. I'm just substituting the values, and then what are we going to do? Then what we are going to do is, we are going to change this a little and finally arrive in this equation. I am going to make f the subject. So when I make f the subject, what will happen? When I make f the subject, I will get an equation like this. N goes up, 2L goes down, n over 2L square root of t over m. One of the most important equations you have to remember when it comes to this lesson. Okay, f. If you want it to be simpler, you can use this also. F is equal to nv over 2L. That is also, you can use that equation also. What have I done here? Instead of root of t over m, I have used v. If not, this is much better for you. This is much better, because when you compare parameters and all, this would be much better. Okay, good. And if n is equal to 1, when n is equal to 1, that will be the fundamental mode. Agreed? Right. So when n is equal to 1, it will be the fundamental mode, and when n is 1, f becomes f naught. So another equation can be written f naught is equal to 1 over 2L square root of t over m. Okay. So this is the equation for any frequency of a standing wave formed on a string. This equation can be used for any standing wave formed on a string, but this particular equation you can use only for the fundamental mode, very frequently used equation. So we have learnt these two equations and the different types of wave patterns as to how you can analyze that. I hope this part is clear to you, and you can find lots of questions in A levels MCQs and all. Okay. Now, where do we find these standing waves? In any music instrument, the sound you hear are because of standing waves. Any music instrument. Let's take the instrument with strings: violin, guitar, ukulele. Ukulele is something like a small guitar in the people have in their hand. In all those, we have these strings. So when you pluck those strings, standing waves are formed. When you when you create standing waves with different number of loops, then the frequencies are different. Okay, different number of loops, then frequencies are different. When the frequencies are different, pitch is different. So if the song is at the same pitch, then the song will be really boring. Different pitches, song looks nice. This is what happens. Okay, different, right? Then you have flute, you have trumpet, you have flute, saxophone, those things. So in that you blow the air, and inside the trapped air, inside the instrument, in the trapped air, in the trapped air, standing waves will be formed. That's another reason. So in any musical instrument, a sound is formed actually due to the formation of standing waves. If they ask you where you see standing waves in day-to-day life, then you can say in musical instruments. The first experiment under standing wave lesson will be this. Now there are 2 experiments in the syllabus under sonometer experiment 1. So this is going to be the determination of unknown frequency of a tuning fork. Now I said there are 2 sonometer experiments. One we do it with just one tuning fork. The other experiment is done by a set of tuning forks. So this is an experiment where we do with one tuning fork, because obviously you can understand it from the title, determination of unknown frequency of a tuning fork. There is a tuning fork, we do not know its frequency. So we are going to find it experimentally using a sonometer. We already discussed what a sonometer is. I will quickly draw it. So next, the first step is the required objects. Now all these notes are available for you in your practical guidebook. So I'll just explain the important parts, and then you can go through that guide and get the theory part, diagram, the procedure, and all those things. There are certain parts we have to discuss. Let's discuss just like we do normally. The experimental setup actually looks like this. First of all, I will draw the sonometer box. So this is the sonometer box. We'll have a box like this, and in the sonometer box, we have already discussed this. There will be 2 bridges which are movable, all right, and then a string will go over that. It will be fixed like this to this point, and that string will go over a pulley like this, and then that pulley will be the string will go down, and it will be connected to a pan like this, where you can add weights. Okay, so you have the weights, and you can actually add weights like this. Okay, why do we add weights? So that we can create a tension in the string, then the string will be stretched, then only we can produce standing waves. Good. Now let's see what we do next. Then what we do is we take the tuning fork of unknown frequency, we tap it on a rubber surface. Ideally, there is this rubber surface in the laboratories which is available. If it is not there, you can tap it on the sole of your shoe, and then you can place the vibrating tuning fork on the sonometer box, like this, not anywhere else. Okay, not on the wire, not just above the sonometer box, on the sonometer box. You have to place it like this. So now the tuning fork is vibrating, and we learnt a type of oscillation, forced oscillation. So due to the when this tuning fork oscillates, what happens is the energy from the tuning fork will first go to the sonometer box, and from the sonometer box the energy will transfer to the bridges, and from the bridges the energy will be transferred to the string. Understood? Energy will be transferred to the string, and then this string will start vibrating. This string will start vibrating like this because of forced vibration. Then we know now this has a frequency, this string starts vibrating, it has a frequency. When you change the length between the bridges, the frequency of the string will change. So at one point the frequency of the vibrating string and the tuning fork will become equal to each other. That's when the resonance takes place. Okay. So when the resonance is taking place, we know the the frequency of the oscillating or vibrating string and the frequency of the tuning fork are equal. So we have to identify the resonating point when does the resonance happen, right? So I will draw the experimental steps here. First of all, you bring both the bridges closer to each other like this. You bring closer. I'm not going to draw the entire thing. Okay, others will remain the same. You bring both the bridges closer to each other. The string will be like this. Okay, right. That's the first step, bringing both the bridges closer to each other. Second step, what you do is you place a paper rider. What do you mean by paper rider? You take a small piece of paper, small strip of small, and then you bend it into half. So, you will get a paper right like this. It will be in this shape, something like this. This is what you call a paper rider. Okay, very if you can make it even thinner, it's better. It should be very light and something like that. You place that paper rider exactly in the middle between the bridges. You place the paper rider like this. Okay, then the third step, what you do is you vibrate the tuning fork, and then you place that tuning fork on the sonometer box. Okay, now the paper rider will be ready. It will be at the center, and the tuning fork is kept on the sonometer box. That is a very important step. I am repeating one over and over again. The tuning fork must be kept on the sonometer box. Remember, the tuning fork is vibrating. Okay. Then what we do is we slowly move the bridges apart. We slowly move the bridges apart. So, we move the bridges apart. The reason is the paper rider will be always at the center. Correct? The paper rider will be always at the center, right. So, at one point we know when this paper rider, sorry, when this string and this tuning fork have equal frequency, this string will create a standing wave like this, and at that time resonance will take place. When is that? When this frequency becomes equal to this frequency. Resonance will take place. When resonance takes place, we know the string will be oscillating at its maximum amplitude. At that point, this paper rider will fly off. This paper rider will fly off, or it will just fall away automatically. We don't have to throw it. It will just fly away because it is vibrating at a very high amplitude. This is when the resonance takes place. When the paper rider flies off, at that time you will be measuring the length between the bridges. So, to do that you will need a meter ruler. Sometimes in some certain sonometer boxes, meter ruler or a measuring scale strip is pasted. Then okay, if not, you will need a meter ruler to measure the length between the bridges. Okay. So, why does the paper rider fly off? Because the frequency of the at a certain length, the frequency of the vibrating string and the frequency of the tuning fork become equal to each other. So, they resonance takes place. During resonance, what happens? This is the driving frequency. Now, the other object which started resonating will start oscillating at its highest amplitude, right. So, at that time you can measure L, and remember this, since this is the first wave formed, it will be in the fundamental mode, alright, fine. So, let us consider this stage here. If I consider that stage here, this is going to happen eventually, this is going to happen, and the length between the bridges is L. Okay, right. Now, what is the purpose? Finding this frequency of the tuning fork. Now, for this case, let us see the theory part. Let us see the theory. Okay, let us start theory. Okay, before that we know this wave is forming just one loop. So, lambda by 2 it's actually equal to L. From that I can say lambda is equal to 2L. Okay, that is where we have to start. Then this mass, let us say it is capital M, and because of that capital M there will be mg, and then here we have a tension capital T, and this tension will be equal to mg. What is the reason? Because this object is at rest, so downward force should be equal to upward force, all these things, right. And yes, let us continue then. The purpose is finding F, and it is happening in fundamental mode. Now, you might have a question, okay, why can't we do this experiment in first overtone? Why can't we do this experiment in second overtone, right? For that you have already know the answer, even though you might be little puzzled. That is because of this. During fundamental mode, the amplitude is high, but during the first overtone, amplitude is slightly less. During the second overtone, the amplitude is even less. Then we don't have to talk about other what do you call that, overtones, right? So, it is very difficult to observe this paper rider flying off unless we have a very large displacement of the string. So, that is why to identify the resonating state very clearly and accurately, we use the fundamental mode, because the reason is fundamental mode has the highest amplitude. And second thing you need to know is we have placed the paper rider exactly at the center, haven't we? That is also again, even in the fundamental mode, only the center part, the antinode will have the highest amplitude. See, the other parts have small amplitudes. So, always if you go, if you can choose the highest amplitude, then you will be able to identify the paper rider flying off conveniently. Then only the experiment will be more accurate. No? That's why we place the paper rider at the center, and we use only the fundamental mode. So, for fundamental mode, we studied an equation f equals 1 over 2L square root of T over simple m. Okay, right. I am going to plot a graph, right? Because we know always it's better to plot graphs, because when you plot graphs, we will be getting several readings. So, we are reducing the errors and we are improving the accuracy. To plot a graph, what do we need? We need two variables. Okay. So, in this system, what are the variables? F can't be changed because F is what we are supposed to find out. But you can change the mass. By changing the mass, you can measure the length, different lengths. When you change the mass, the tension will change. When the tension changes, the length, so frequency will change. Accordingly, we have to change the length also. Do you agree with me? Yes. So, if you come to this equation, we have to find F, and L is there, right? Fine. Who is under our control here? Capital M is under our control, correct? I can change M 100 gram, 200 gram, 300 gram, 400 gram, like that, and for that I can measure the corresponding length L. So, L must be in y axis, and M, the mass of this, the weights we are using, should be in x axis. If not, in other words, L is going to be the dependent variable, M is going to be the independent variable. Okay. With we know the dependent variable must be brought to the y axis. So, I will make L the subject. When I make L the subject, I will be getting L equals 1 over 2f square root of, instead of t, I will substitute mg, okay, capital Mg over simple m, right. And then since there is root, things will get little complicated. Let us square either side. So, I will be getting L squared equal 1 over 4f squared mg over simple m. And I will rearrange this equation, and I will end up in an equation like this. L squared is equal to simple g over 4mf squared into capital M. I hope you can agree with me on this. It's just a matter of rearranging. So, when you have a look at it, you see it has the form y equals m x, where capital M will be in x axis, L squared will be in y axis. Actually, L squared is going to be our dependent variable in the sense L squared is going to be in our y axis. So, the readings we are going to take for different values of m, okay, we are going to measure L values. Now, m will be in grams, or let us say in kilograms, and we are going to measure L in centimeter or meter, and L squared is going to be in meter squared. So, for mass you can choose values accordingly. Those values will be given to you in the guide, 0.1, 0.2, 0.3, 0.4, 0.5, 0.6. When you choose these weights, you have to be careful. There is a possibility of this string breaking. If the string breaks, it might be an accident. Sometimes a broken string might get thrown away and hit someone on in the eye. So, you have to be absolutely careful when you choose these weights. So, you have to follow the instruction of a teacher and choose the weights wisely. And then for where you add first 0.1 kilogram is 100 gram. You add 100 grams here. You do these steps and find the length. Then you add 200 grams here. Do these steps, get the new length. Likewise, you measure all the lengths. Then you get L squared values by squaring the lengths you measured, and then what do? You plot the graph. You plot the graph while taking L squared on y axis, meter squared, and capital M on x axis. So, when you plot the graph, you should be getting a straight line like this. You will get random point. Initially, you will get these random points, and then you will choose the best fitting curve and you will go draw the graph. Okay. Now, from the graph, we know we can take some results. That is, from the graph, you can get the gradient, correct? When you take the gradient from the graph, the gradient will be equal to this, simple g over 4m f squared, 4m f squared. So, f is what we are supposed to find out. F squared is going to be equal to g divided by 4m multiplied by gradient, and from that you can say f is going to be equal to the square root of that. G over 4m into gradient. Okay. Now, G is okay, it's 10 meter second minus 2, or else if you want to be very precise, 9.81 meter second minus 2. Gradient you can get from the graph. How do we get a gradient from a graph like this? We choose 2 points on the line as far as possible. You can't choose these points, the red dots. You have to choose 2 points on the line, and then when you choose those 2 points must be as far as possible, and then this is the difference, we take it as delta y, and this difference we take it as delta x, and the gradient is delta y over delta x. That is how you get the gradient. These things we have discussed earlier also. From that you will get this, and m is the mass per unit length. So, what you do is you remove this y after the experiment, you measure the mass. So, you will need an electronic balance, and then you measure its length using a meter ruler. Then when you divide that mass by length, you will be getting mass per unit length. If not, we learnt another equation for mass per unit length. I hope you can remember, m equal to a rho, if not pi d squared over 4 rho. Mass per unit length is equal to pi diameter squared over 4 into rho. Rho is the density of the wire. So, if you know the density of the wire, if you know the material of the wire, you know the density. Then using a micrometer screw gauge, you will measure the diameter of the wire at different places. Perpendicular to, at one place you take 2 readings. You take a reading like this, then you rotate it by 90 degrees, you take another reading. Likewise, at least at 3 places you should take readings. Altogether you will get 6 readings. You get the average, then you will get the average diameter. Using this equation also you can find m. It depends, according to the question you have to adjust and get the answer. Okay, right. So, this is how it works, the experiment works. Now, normally there are few things we have to discuss. No? Discussion is the most important part when it comes to an experiment. All the notes, all the procedure, it's available for you in your practical guidebook. So, don't worry about that. Now, when it comes to other important factors, now I'll quickly do a recap of the important factors. You have to bring both the bridges very close. Why is that? Now, you don't know where the first resonance will take place now. So, you don't want to miss that out. Because sometimes if you start at a position like this, let's say, then you might miss the first resonating point. No? So, we do so for not to miss the first resonating situation, for the first standing waveform, we have to start from 0 length, or else from a very small length. This is not 0, actually very small length. That is the first reason why we bring the bridges close to each other. Second reason, we use this paper rider to identify the resonating state, and we place the paper rider, we always maintain the paper rider exactly in the middle between the 2 bridges, because when a standing wave is formed, the amplitude is maximum at the middle, so that you will be able to see it flying off conveniently. So, the practical will be more accurate. Second, I discussed this also. Why fundamental mode? Because during the fundamental mode, the amplitude is maximum. So, again, identifying the resonating states will be easier and more accurate. And the other thing, they will ask you which tuning fork will you which mass will you choose first? Will it be the highest mass or will it be the lowest mass? Now, when you use the lowest mass, let us say 100, you add 100 gram first, then you will measure a length. Look at this final equation. Okay, when you increase the mass, length is going to change, length is going to definitely increase. No? So, when you use this mass in ascending order, for 100 gram, let us say the length is 10 centimeter, for 200 gram, let us say the length is 13 centimeter. So, when you add 100 gram, get the length 10 centimeter, you add another 100 gram, you do not have to do this again. Why is that? Because we know definitely the next length is going to be greater than 10 centimeter. So, we can without bringing the bridges closer, we can keep on moving from the initial position itself, second length, third length, fourth length, that is an advantage. And sometimes we use the highest mass to find out whether the last length can be taken in this sonometer wire. Because now see, now this sonometer box is relatively longer than this, but let us say this is the sonometer box we have. So, maximum length might be somewhere here, right, somewhere here. But if this length we are supposed to measure is greater than that, then we are in trouble, correct. So, what we do is, sometimes we add the highest mass first, and check whether the length of the sonometer is enough to get that final reading, and then we start from the beginning. So, those are some small aspects you have to know. A very common question we get in our model papers and everything. So, you have to be ready. And one more thing, you have to place the tuning fork on the sonometer box, not on the string, not anywhere else, on the sonometer box, because when you place it on the sonometer box, the energy transfer will be maximum. If you place it somewhere else, the energy transfer will not be maximum. If the energy transfer is not maximum, it is difficult to identify the resonating state. So, that is another point you have to know. Okay, the other things you can read in your practical manual, and if you have any doubts, you can ask me later. The second experiment under sonometer will be determination of speed of a transverse wave along a string. So, we are going to find out experimentally, we are going to find out the speed of a transverse wave along a string. That is what we are going to do in this experiment. Again, we are going to use the sonometer. The early experiment, we use one tuning fork. In this experiment, we are going to use a set of tuning forks, and we are going to plot a graph and get the results. Let us see the experimental setup. So, just like the previous case, we have to draw a sonometer box. These things are important. Sometimes you might have to draw these systems. Okay, so pay attention and try to draw on your own later when you copy the notes. So, the sonometer box, the bridges, and then the string, and here the string will be passing like this, we know that, but we are not drawing it, and then the string will be going like this over a smooth pulley, and then there will be the weights. Okay, we have this pan where we can hang weights. So, I will just draw the weights like this. We have the weights. Okay. In the early experiment, what we did was, by changing the weights, the mass of the weights, we measured the length. That is what we did earlier. I will take the mass of this as m. So, there will be mg downwards, and there will be a tension created here, and that tension is equal to mg, settled. Okay, fine. In this experiment, the purpose is finding the speed of sound in air, speed of transverse wave along a string. For that, what we do is, we are going to change the frequency of tuning fork. For different tuning forks, we are going to find the resonating lengths. Now, we have already discussed what is resonating length, how to keep the tuning fork, why do we keep like that, where do we keep the paper rider, all those things we have discussed in the earlier one. So, here also same thing is going to happen when this frequency and the frequency of the standing wave created on the string become equal, we know there is going to be resonance. So, this standing wave is going to be formed, right, and just like the earlier case, we will be measuring this length L. We will be measuring this length L, and the frequency of this is F. Okay, right. So, in this experiment, we do not change this weight. Instead, we change the frequency of the tuning forks we use, and then we measure the corresponding lengths. So, let us try to build up the theory part. Before that, we know this is one loop. We always go for fundamental mode. Why is that? In any sonometer experiment, it is always fundamental mode. I want you to remember that, because fundamental mode has the highest amplitude, so that it is easier and more accurate when you find the resonating state. We need the paper rider to fly off. Paper rider will not fly off if this amplitude is small. It will, when I say it will not fly off, it will be very difficult to get to that situation accurately. Okay, so always fundamental mode. When the mode is fundamental, we know one loop, so the wavelength is lambda by 2, and that is equal to L. That gives me lambda equals 2L once again. So, this is not new, last time also we came across this. In this experiment, the theory part is very simple. In the theory part, we use the equation V equal F lambda, nothing else, V equal F lambda. V is what we are supposed to find out, equal to F is the frequency of the tuning fork into lambda is the length. So, it is 2L. Now, there is a small issue. Both F and L are on the same side. So, L or F, both F and L can't be the variables. You will have to take one to the other side, and you can see F is our independent variable because F is under our control. The frequencies, because they will give you 6 tuning forks in one set of tuning forks. So, the frequency values are fixed, and that is not measured, that is already known. but the lengths we have to measure and get. So, length is dependent variable and frequency is independent variable. Alright. Now, I will make L the subject. When I make L the subject, the equation will be rearranged to something like this, V over 2f, okay, V over 2f. So, what we do in this experiment is we take L equals V divided by 2 into 1 over f. This is our equation, final equation we get, and you already know this equation looks like y equals mx. So, this is the y axis component, this is the x axis component. Do not forget to show this once you get this equation in structured questions, because I can remember in one of the provincial papers they had given marks for this part as well, identifying the variables like this. So, always practice this, if not you might lose some points. It will take just few seconds, do not forget that. Sometimes it is y equal mx plus c, sometimes it is y equal mx minus c, sometimes it is y equal minus mx plus c, you know, different cases. Just be a bit careful. Good. Now, what are the readings we are going to use? The readings we are supposed to take are, obviously we start with the frequency of the tuning forks in hertz. So, you know the values. We just write one value 256 and then some other values, some other value 1, 2, 3, 4, and finally 512. I think when I was explaining tuning fork, I told you these are the minimum and maximum values. That is not enough for you. You need to find out 1 over f. So, when you find out 1 over f, the unit will be second. I don't know whether this is clear to you. Hertz can also be written as second minus 1, because frequency is 1 over period of oscillation. So, this is second minus 1, the reciprocal of that can be taken as second. You will find that, and then you will, for these different values of f, you will have to measure the length L. Okay, right. So, these are the readings, and one more thing you have to be very careful about this experiment is this. When you increase the frequency, the resonating length we obtain will reduce. Okay, when you increase the frequency, the resonating length will reduce. So, initially if you want this length to be smaller, that means you have to go for the highest frequency. I hope you understood what I said right now, because I explained in the previous example also. If you are going to measure the lengths in increasing order, then you do not have to bring these bridges closer to one another again, right? You get a first length, then if you are sure about the second length being greater than the first length, from that position you can keep on increasing the gap between the bridges, which is the logical way to do. So, in this experiment you have to start with the larger tuning fork, and you have larger tuning fork with the largest frequency, and then you have to go in descending order if you want to get the lengths in ascending order. I will repeat. According to this equation, you can see when the frequency of the tuning fork is large, the resonating length will be small. We want to obtain the resonating lengths in the increasing order. Okay, if you want the resonating length to be in the increasing order, the frequency of the tuning forks must be used in the decreasing order. So, this is going to be your first tuning fork you are going to use, and this is going to be your the sixth tuning fork you are going to use. I just wrote it because naturally it came to me that way, but keep this in mind. Okay, these are questions, and then they will ask about the experimental setup. I am not going to draw that and explain it to you. I have already explained it to you. What do we do? First of all, you bring these two bridges close to each other. Then you keep the paper rider such that the paper rider is always at the center between the two bridges. Then you vibrate the tuning fork and place it on the sonometer box. Okay, you place it on the sonometer box. Please make notes about the important things I am telling about this experiment. It's very important, because those the questions in the structure paper will be based on these important facts. Then you will move the bridges apart from each other until the paper rider flies off, and when at the moment the paper rider flies off, you will measure the distance between the bridges, and that will be L. And then what do? You change the tuning fork. Now, you start with 512, the next one may be 480 if I can remember, right? For that you measure the new length, then you change it 384, you change it likewise, you keep changing the tuning fork and you keep measuring the length. If you use the tuning forks in the descending order, the advantage is you will get the resonating lengths in the ascending order What is the advantage of that? You don't have to bring the bridges back to their initial positions. You just can continue from the previous position. Okay, that saves time in the experiment. Good. Apart from that, again we discussed, we use only the fundamental mode. The reason is in the fundamental mode only we get the highest amplitude, and also we always place the paper rider at the center of the standing wave created. Again, reason, at the center of the standing wave the amplitude is maximum. Okay. Well, we did not continue after this. We have to plot the graph now. So this is going to be in x-axis. This is going to be in x-axis, and this is going to be in y-axis. Okay. So the graph we are going to plot is going to look like this. Y-axis, so length in meters, and x-axis 1 over f, and that will be in seconds. Okay. Then when you in the subsequently you will get a graph like this, and you know the points will be arbitrarily arranged. And when you want to get the gradient, what do? You choose 2 points on this line as far as possible, then you find the gradient. Okay. When you find the gradient, what does the gradient tell? Gradient in this question is equal to v by 2, where v is the speed of transverse wave, v over 2. So finally v is equal to 2 multiplied by gradient. A very easy conclusion. Let's say you want to get a different you're doing the experiment with same set of tuning fork, but you want to get different gradients of graphs. Then what do you have to do? If you want to change the gradient, you have to change v, and we know v is equal to square root of t over m. This is the equation for v. So if you want to change v, you can't change m because we are using, let's say we are using the same string, so we can't change it, but we can change t. How is that? By changing the capital M we are using, the weight we are using. So when you increase the weight, that means the tension will increase. When you increase the weight, the tension will increase. When tension increases, speed will increase. When speed increases, the gradient of the graph will increase. I hope you understood that. Let's say there are two graphs like this, okay, A and B graphs, and you can see graph A has a lower gradient, graph B has a higher gradient. That means speed of transverse wave in string in the experiment A is greater than speed of transverse wave in experiment B. If you want that to be high, that means tension in the string during experiment A is greater than tension in the string during experiment B. That means the mass of the weights we used in experiment A must be greater than the mass of the weights we used in experiment B. I am putting capital M, not simple M. Capital M is the mass of the weights we use here. Simple M is the mass per unit length. Well, I hope that part is clear for you, and yes, this is it. Most of the parts were covered in the previous experiment. I just summarized them again. I am not writing any notes or paragraphs. All are available to you in the practical handbook. Listen to this tutorial carefully, and if there is anything missing in the discussion parts or notes part, please add those to your practical guide, and if you have any doubts, you can ask me.